Okay, we had several people ask about chi-squared help, and mainly they were looking for identifying the chi-squared. This video, I'm going to go through several different chi-squares and do so very rapidly. If I have opportunity, I will show later videos where I actually work them out. For right now, I'm only going to be breaking down how to do the test, etc. Most of this you can read by yourself, so I'm not going to do it. I highly recommend you print it out if you're struggling with chi-squared and take a look at it. One thing I want to remind you is if they give you a chi-squared value, and let's just say they give you a chi-squared of 12.6, and either they give you the degrees of freedom, or they tell you how to, or they give you the information to calculate, not the degrees of freedom, to calculate the degrees of freedom. Either they give you the degrees of freedom or they tell you how to do it, or give the information so that you can do it. You can calculate the p-value. So here's what you need to know. You can go second, bars, scroll all the way down. I'm not even seeing it. There it is, chi-squared CDF, it's number 8. And I said I had a 12.6. All right. And then it's always going to go to infinity because it's skewed to the right, positive. And let's just say we happen to have a matrix that looked like this. 1, 2, 3, 1, 2, 3, 4. So we had a 3 by 4. So 3 minus 1 times 4 minus 1. This is 2. And 2 times 3 is 6. So we'd have 6 degrees of freedom. And I end up getting a 0.049 p-value. So it calculated my p-value for me. And that's if they gave me the rows and columns, or a way to figure out the rows and columns, or if they told me the degrees of freedom. So real quickly, we can go second, vars, scroll down to number 8, chi-squared CDF, because we never use the PDF in this class. We put in the chi-squared statistic. Upper bound is always going to be infinity, and degrees of freedom is whatever we calculate or they give us. Okay, the formula for all chi-squareds is this. If it were me, I would never ever name the chi-squared. I would never use the word chi-squared test of homogeneity. I'd never say chi-squared test of independence. I never would say chi-squared goodness of fit. I would write chi-squared and I'd write my formula and that'll work. Please remember, O is observed values, E is expected value, and N is the number of different data cells or categories. The number of categories is a better phrase. This says simple random sample, really just needs to say random sample. These are our Goldilocks. N is less than 10%. Expected value is greater than 5. The rest of this you can read. So let's take a look at a problem. So you all probably recognize this because it's very similar to the test question if it wasn't the test question you had. The product advertisers studied the effects of television ads on children's choices, et cetera, et cetera. And I'm going to speed through this so you don't have to watch a long video. You can read it yourself. There was a line here. I don't know why it didn't print out. So real quickly here, I look at this and I go, I have a table of values. I see table of values. I'm going, since I have multiple categories, 1, 2, 3 here, and two categories here, I'm going, you know what? This is not going to be a proportion, because if it only been 2 and 2, it might have been proportions. But when it becomes this 3 and 2 or more, can't be proportions. So this is going to be a chi-squared test. The question is, what type? So I need to sit there and continue reading and look to see if there's n. And it says, do the data provide convincing statistical evidence that there is an association? By the way, if there is an association problem, it can only be one of two things. It can only be chi-squared independence, or it could be a regression. All right? We're almost guaranteed not to have to input data for regression, but even if we did, it would need to be a longer list, and these would be able to need to be defined as an X and Y. So this is not a regression. This is a chi-squared test of independence. My keyword is what gives my table, and the keyword of association gives that away. All right, next problem. Once again, I'm not going to go ahead and read this thing, but I am going to look at it. So they've established acceptable wait times. So here's the probability of wait times. And it's like, okay, this is what they want to have happen. All right. And we notice we have 1, 2, 3, 4, 5 categories here, 5 categories of wait times. And over here, we have a matching the exact same categories. All right. And then it says, okay, so we have the exact same categories. And notice I have whole number counts. And that's the other thing is, I should have said that earlier, you're going to have whole number counts all the way through. Use the sample data for the customers to conduct a statistical test determining if the wait times in new branch are inconsistent. In other words, consistent or inconsistent with acceptable probabilities for the waiting time categories. So they want to see if they are the same or different, because the word inconsistent goes, hey, are they the same or not the same, or are they the same? As soon as they're saying same or inconsistent or matching, et cetera, do they match? If they're asking us if they match, then this is going to be a chi-squared goodness of fit. Now you're like, well, how do I know first off that it's a chi-squared? Well, the very first thing is I have multiple proportions here or multiple probabilities. And I don't have any way to handle multiple sets like this unless I put it into a chi-squared. No other test will do that. No other type of test will do that. If I only have 2, I could work with a 2 proportion test, but I have more than 2. As soon as I have more than 2, I'm out of luck. So can't do a proportion, I have to do chi-squared. Now, I also know it's a goodness of fit because I only have 1 row of data. And you're like, wait a second, no, you have 2 rows or 2 columns. No, I only have 1 column. These are not counted data. So if this is not counted data, because this is not counted data, there's no way that counts as a column of counted data. So I only have 1 column of counted data, and here it is. And because I have 1 column of counted data, because chi-square goodness of fit will either be either 1 row or 1 column of column data, counted data. Either it'll be 1 column, which is what we have here, or it'll be 1 horizontal row of counted data. This is what I need to match to, okay? We will work this problem, so I'll do this problem in another video. Moving right along. My favorite moose problem, okay? So here we have 4 different categories. And as I scroll down or slide this thing up, I'm looking and go, oh, I've got a table. Wow, as soon as I have a table, probably chi-squared if they're going to have me run a test. Matter of fact, I know it's going to be chi-squared if they're having me run a test, or most likely going to be. So I'm going to read this thing and see what it says. Researchers who are conducting this study expect the number of moose observed in a habitat type to be proportional to the amount of acreage of that habitat. Are the data consistent with this expectation? Conduct an appropriate statistical test. So we know we have to do a stat test to determine whether or not it's proportional. Okay, so my question to you is, first off, I see proportional, I go, you know what, the word proportion, this could be one of those homogeneity tests. We haven't seen one yet, but this could be it. But then I look at it and I go, oh, wait a second. This is not counted data. Only this column is counted data. So I have 1 column of counted data. So 1 column of counted data tells me it is a goodness of fit. If it's 1 row of counted or 1 column of counted, it's a goodness of fit test. So this is a goodness of fit test. And so what is this? This is the expected proportions. This is the projected, or this is the proportions proportion of acreage. So basically we would expect to have 34% moose. We'd have 10% moose, 10% moose, 45% moose, and that would make 100%, which is what we have here. We would expect it to be proportional or consistent or matching. Do the proportions match? But once again, I only have 1 column of counted data. 1 column or 1 row, it's a goodness of fit. The next problem. Again, I have a table and I look at it and I go, oops, this is 1, 2, 1, 2, 3. This is a 2x3 matrix. 2x3 matrix. And guess what? Every single one of these are counted data. If everything's counted data, this is going to be a chi-squared, and it's not going to be a goodness of fit because I have 2 rows and 3 columns of counted data, unless they're asking me, do they match? So I better check to see if they're matching first. If it's matching, then it's going to be goodness of fit. But if they're not matching, something else. So do these data provide convincing evidence of an association? That's the key word, chi-squared independence right there. All right. And once again, I had multiple rows, multiple columns. It's like, yep, chi-squared. And then I see the word association, therefore it's independence. Next problem. And then once again, I have 2 rows and 1, 2, 3, 4, 5 columns. So this is a 2x5 matrix. So guess what? If I have to run a statistical test, I can't do it with anything but a chi-squared because I have multiple rows and multiple columns, or multiple 2 categories and 5 categories. Can't do it. So here we go. Is there sufficient evidence to indicate the response is, oh, keyword, dependent. If I see dependent, this is going to be a chi-squared independence because there's one of those key words. Now let's look at this. If they said males match the females, that would be different. Then we might be into a problem. That might be goodness of fit. But here they want to know, are they dependent? And since they're saying, are they dependent? The answer is no, right? Test for independence, if they say, do the proportions match? If they say proportions match, it's goodness, I mean, proportions match, then it's going to be a homogeneity. They did not say proportions match. They want to know if it's dependent. Here it's dependent. So that makes it a test of independence. And once again, I have 2 rows of counted data and 5 columns of counted data. If I have more than 1 row or more than 1 column of counted data, it's not a goodness fit. Once again, more than 1 row or more than 1 column, it's not a goodness of fit. All right, so this problem here is a very long problem and actually starts off with probability. So I'm going to skip the probability part and drop down to part C. And part C says, and here we go. First off, we should look at the wheel. This is what the wheel should be, and this should be 0.25, 0.25, 0.25, and 0.25. That should be my probabilities. Okay. So, a contestant who lost at the game alleges the wheel is not fair. In order to check on the fairness of the wheel, the data in the table below were collected for 100 spins of the wheel. Based on these data, can you conclude that the 4 outcomes are not equally likely? So what do they want to know? Well, first off, how many times did we spin it? 100. How many, what's my expected value? 25, 25, 25, 25. These are my expected, because it's 25% of 100, 0.25 times 100, or 100 divided by 4 if you prefer. But I actually have 1 row of counted data. That's not counted data up here. Yes, you can win $100. These are categories. These are the categories. But my counted data, I only have 1 row. So 1 row or 1 column is a chi-squared goodness of fit. And this is a chi-squared goodness of fit because I only have 1 row of counted data. I only have 1 row of counted data. Moving right along. Immediately, I see a table. And I'm going, well, all right, if I have to run a hypothesis test. If I have to run a hypothesis test, This is probably, now this, I have to be careful here. This has totals. So it's possible that we're looking for a two proportion test. It is possible because I have 2 rows and 2 columns. And with 2 rows and 2 columns, we could be running a two proportion test. So we need to read the question to see what it is, because this really is tricky. This could be done as a two proportion test, depending on what they ask. And they ask, is there an association? This is either because we can't count the totals. All right, we have a 2 by 2 matrix, and a 2 by 2 matrix could be proportions. Read the question. It says association. Guess what? Chi-squared test of independence. If it hadn't said association or dependence, and first off, because we have 2 rows and 2 columns, this cannot be goodness of fit. Can't be goodness of fit. Goodness of fit can only have 1 row and 1 column. This can only be two proportions or homogeneity or independence. And since they said the word association, chi-squared test of independence. Finally, they're going to ask you to draw a graph here. That's no big deal. But if we look at this, I have 2 rows and I have 3 columns. Excuse me, I said that wrong. 3 rows and 2 columns. So this is a 3 by 2. So I immediately know it can't be proportions. I also know that it can't be goodness of fit. There's no way this can be goodness of fit because I have too many. So that can't be this one because I have 3 rows and 2 columns. One of those has to be a 1 in order to be goodness of fit. That said, the question is, could it possibly be 2 proportions? We'd have to look for the way the question was phrased, but unlikely. Here we have the word association. So that makes it a test of independence. All right. And the only reason I say it's unlikely, they would have to say, is the proportion of people who never had a job, people who never had a job different from males than for females? Then I could compare the proportion for those who never had a job. But if I want to know job and gender experience, okay, so 2 proportions, all right. Well, hold on, let's deal with chi-squared first. Chi-squared, 1 row or 1 column, goodness of fit. And the keywords there are matches, consistent, same, follows the specific distribution, follows the uniform distribution, follows the normal, follows the geometric. Doesn't matter. It has, or follows the historical even, or matches. Okay, those words indicate goodness of fit. Multiple columns, at least a 2 by 2 matrix. It could be 3 by 2, 5 by 2, 5 by 4, anything with multiple rows and multiple columns. Then we are looking at a test of independence or homogeneity. And really, they run the same way. You don't have to name them. Just write down chi-squared and write down the formula. But when I look at something like this, it's like, you know what? I could be comparing male and female. Read the question. Between gender and job experience. So I'm not looking at just one. It'd be gender and never, gender and had, sure, gender, or had a part-time job, but only during the summer, or not during the summer, or whatever. I can compare this to this as a proportion, or this to this as a proportion, or this to this as a proportion, but I cannot compare these 3 categories. So with the 2 proportions, I can only compare 2 categories to 1 category. All right. So I can do a 1 by 2 or 2 by 1, however you want to look at it. All right. I'm going to, in the next videos, work a couple of these out, but not all of them. All right, thank you.